In this video, I'm going to give an example of a sampling distribution for a sample mean, and then also a little bit on how you do this for a standard deviation. So this comes from section 6.4 in our textbook, Sampling Distributions and Estimators. And the whole idea is that you're going to start with a very tiny little population, take samples from that population, and then build a sampling distribution based on those samples. Now, in the grand scheme, you're not going to be doing this if you have a statistics job. You're just going to go out and take your sample and then do your calculations on it. But the big idea is that this happens behind the scenes so that the sampling distribution does exist, and now you know how it got created. So when you go out and take your sample, you have an idea, oh, this is where the sample belongs in that distribution. And then the goal is to figure out, well, the sample that you did take for your job, how likely was the average of, 15 supposed to be occurring? You'll be able to tell that based on some facts about your sampling distribution. So let's start off with our population. Instead of just giving some numbers, I'm going to give a little bit of context here, just to make it a little bit more believable. So let's say that we have a neighborhood, and on this block there are families that have 1 kid, 3 kids, and 4 kids. So I've drawn a picture of the population right here. Population. And I've graphed it out in this histogram. The frequency is 1 because we only have 3 families. And the family with 1 kid, 3 kids, and then 4 kids is only seen once. So the next thing to do is compute our population mean. So I did that already. I added up 1 plus 3 plus 4, so that makes 8. Divide that by the 3 families. So I'm getting 2 and 2/3. So almost an average of 3 kids per family, but it's just a little less than 3. So I computed this population mean because I'm going to compute a mean later on, and I want to come back and be able to compare these together. So this is our population mean. So you could say mu equals 2.67. Now this is the number that you don't actually know, because if you did know your population mean, why are you doing statistics? This is the unknown number that you're trying to estimate. This is unknown. You're trying to estimate it by taking samples. So let's say that we want to take samples of size 2. Now I'm choosing size 2 because it's pretty easy to compute sample means. It doesn't get overwhelming. The larger your little population is and the larger the number of samples, the more complicated this gets. So that's why all those homework problems showed taking maybe a sample of a sample of 2 or maybe 3, but they kept it pretty small just to keep it manageable. So to take a sampling distribution, to create a sampling distribution for a mean, we need to go through and take every possible sample of size 2 and then find the mean of that sample. And then we're going to take one more step and do a graph just to see how all those sample means line up. So down here, I see my population. Let's just write it again. Population where the values 1, 3, and 4. So when you're taking samples, you want to take every combination of numbers. So you pick a number and then you start again fresh and then you pick another number. So I'm going to make a table just like we have seen in the textbook. We have the sample, and then I'm going to compute the sample mean. And then I'm also going to show the probability of getting that exact mean. So for our first sample, we'll take 1, and I'm doing this in a very organized way as well. And then let's suppose we started again, and we got another 1. So that means the sample mean of a 1-kid family and a 1-kid family is 1. Then we could have a 1-kid family with the 3-kid family be selected, and then the 1-kid family and the 4-kid family. And now I've sampled everything possible with a 1-kid family. It's the 1-kid family with everything else. Now I'll compute these other two means. So the average of 1 and 3 is 2. The average of 1 and 4, so let's see, that adds up to 5. That mean is 2.5. Now I'll continue on with the 3 with all three numbers. So 3 with the 1, 3 with the 3, 3 with the 4, and then compute the means. So let's see, that's a total of 4. The average is 2. Average of 3 and 3 is 3. The average of 3 and 4 is 3.5. And then lastly, I'll take the 4-kid family with all three numbers. So the first, we have the 4, the 4, the 4, and then it would get paired up with the 1, the 3, and the 4. This is what I mean by doing this very organized. You can see I went through the 1s and then the 3s and then the 4s with all three values. So this is how you can tell that you're going to have 9 possible samples, because you could have 3 numbers for the first slot, 3 numbers for the second slot, and 3 times 3 makes 9. So 3 times 3 makes 9. If you had 4 in your population, then you'd have 4 times 4, you'd have 16 samples, and that's where it gets, a little out of hand already. All right, back to computing these means. So the average of 4 and 1, let's see, the total's 5, so that's 2.5. Notice that I'm dividing by 2 because I have 2 numbers in my sample. The average of 4 and 3 is 3.5. The average of 4 and 4 is 4. All right, so since each one of these is a sample and we have 9 samples, each mean can happen 1/9 of the time. So for every single one of these outcomes, we have a 1/9 probability. Now, I am going to do one more thing with those means in a second, but let's just write out the 1/9. Each outcome, 1/9. Now you'll notice that some of these means do repeat. Like the 2, I actually see it once, twice. So when you're making your sampling distribution, so finally I'm going to get to the graph, I do care about how often those numbers repeat. So I will make supposedly a straight line. Maybe I'll fix that. Okay, let's try this again. There we go. So my sample means, let's see, there was a 1. And I'm going to, how do I want to do this? Let's do 1, 1.5, 2, 2.5, 3, 3.5, and then 4. So now I'm going to make a histogram with all of the numbers from my table up here. So I noticed that there's the number 1, and that only happened 1 time. So I will just make a box with the height of 1. So I could emphasize that this is 1, this is 2, this is 3. These are my frequencies. Okay, and so I've used that number, I've graphed it. Now let's count the 2s. Let's see, is there a 1.5 at all? Nope, it didn't look like there was a 1.5, but there's a 2. I see a 2 once, twice. So that means here at the number 2, make a bar with a height of 2. And then let's get another one in there. We have 2.5. Once, twice, so 2.5, same height. And then we have the number 3. Let's see, oh, that just happened once. And let's keep going. Then there's 3.5, and 3.5, so that happened twice. And then lastly, we had 4, that happened just once. All right, so this is our sampling distribution. This is the official sampling distribution. We have looked at every possible sample, computed all the means, and then graphed them. So now if you go ahead and let's say go to this neighborhood and then take a sample of 2 and you're like, wow, I got an average of 4 kids, you would know that it's at the tail of this distribution. It's probably not very likely to occur. 2 or 2.5 or maybe 3.5 would be a more likely average for this neighborhood. So this was maybe a little slow because I was working by hand. I'm going to do this by StatCrunch and get this distribution very quickly. This will work really well if you have to do a sampling distribution with a standard deviation or a range or something else. With the average, maybe not so difficult. So here I am in StatCrunch, and the way that I'm going to lay this out is I'm going to put the first number in my sample here in the first column, and then the second number in my sample in the second column. So I'm basically copying these numbers right here, but they're going to go in the column. So I'm just going to do this fast. 1, 1, 1, 3, 3, 3, 4, 4, 4. And then in the second column, I'll go 1, 3, 4, 1, 3, 4, 1, 3, 4. So as you look in a row, those were the 2 numbers that were sampled from the population. So you got a family of 1 kid, family of 1 kid again. Here we got a family of 3 kids and then a family of 1 kid. So now I can get the statistics. So let's go to Stat, Summary Stats. And this time we're going to do it in rows because my data, my pairs were in rows. They weren't in columns. Yes, the data do look like they form columns, but the meaning of the numbers were in the rows, not in the columns. So we're going to go to rows, select var1, and then I'm pushing command and pushing var2 so that it knows where to get my rows from. Even though it does say row statistics and it says select columns, it's knowing to look in each row to find your sample means, not the columns. And then down here in statistics, I just want to compute the mean. So I'll click on mean. And because I'm going to do another sampling distribution at the same time, I'm going to push command and then standard deviation. So I'm just going to kill 2 birds with 1 stone here. And for each sample, I will compute the mean as well as the sample standard deviation. And then lastly, check the box Store in Data Table, because this will take the numbers from the box, all those averages and standard deviations, and put them into the table, meaning it's really easy to make a graph afterwards. So after that, let's push compute. All right. So what we see here, we can close this box. It just said what it did. When I look at this output now, let's see. Yep, that looks good. Here I have each sample in the 2 adjacent columns, and then it computed the row mean, so the average of 1 and 1 is 1, and then it computed the standard deviation. Well, if you have the same numbers, your standard deviation is 0. And then if you had a sample of 1 and 3, the average is 2, and then the standard deviation of the numbers 1 and 3 is about 1.4. So we're looking at each row as our interesting, our pairs of data. I'm going to clear that there. Okay, now I can go ahead and make my graph. So you can see how this table looks like what we did by hand. Here's the row mean. I don't need the probability because the computer is going to deal with that side for me. So let's make a graph. I'm going to make a histogram of the means, and then while I'm at it, I'll just make one of the standard deviations too. Start the bins at, well, let's just ignore this for a second. Actually, let's make them widths of 0.5. Who cares where they start? Let's just make the widths 0.5. And then, I think this will be good. And we'll just push compute. Okay, so here is our histogram of the row means. And let's just do a little double check here. Let's bring this over so we can see them at the same time. So here was our graph that we did by hand, and here it was by computer, and you can tell that, hey, they look pretty much the same, so that's good. If we click on this little arrow here, we will get to the standard deviation sampling distribution. So notice with this row standard deviations, there's a peak over here. There are 3 standard deviations that were somewhere between 0 and 0.5, and then it skewed to the right. But with this distribution, it was, well, there was a low spot here on the left, and then it kind of went up, and then there was this little peak. It's not exactly normal, but it does have low parts on the end and a little bit taller in the middle. So the idea is that when you take a larger and larger sample, this sampling distribution for a mean is going to get more and more symmetric. That's because sample means are really good estimators of population means. We use the word unbiased, meaning that the average of these averages, well, let's in a second compute that. That number is going to be a little bit familiar. Over here with the standard deviation, this is actually a biased estimator. The standard deviations all in here, when we look at the average, it's going to be different than the population standard deviation. So all of these estimates, they're estimating actually a little bit low. And you can tell that they're estimating low because there's a peak over here on the low side. All right, so let's move this graph over here. I want to compute some means. So I know I have means, and I'm computing the mean of means, which is a little confusing, but if I'm looking over here at this histogram, I basically want to know what the center of it is. So I'm going to go to Stat and Summary Stats, and with the columns, with the row means, so this is the means here, I'm trying to find the average of those means. So I'm just going to click mean. I don't really care about the other stuff, and push compute. So this column had all 9 of my means. The mean of the means was 2.666667. So that should look pretty familiar because I'm going back here to our population and we already computed the mean and we knew it was 2.67. And here I am with my sampling distribution. The mean of all these numbers here in the sampling distribution is also 2.67. So that's what we mean by unbiased. The mean of the means is the same as the population mean. And that's why we like sampling distributions, because if we can create one or pull data from one, then we would know that the mean of that is similar to the population. So you don't have to know your population mean. You just have to be able to take samples or maybe have some facts, and then those means will be equal. I'm going to do one thing right here. I'm going to put our population in. I didn't do this before, but 1, 3, and 4. Let's take some statistics on that population. So the population, it was in var 6. And I want to know the mean and the standard deviation of that population. So here we go. There's the mean again. I'm going to get rid of that box. The mean of the population, the standard deviation of the deviation of those values in the population. Now I'm going to do one more calculation, and that's on these standard deviations. Let's see what happens to it. So we'll go to Stat, Summary Stats on the columns. This time I'm choosing row standard deviation. And let's compute the mean of these numbers here in the row standard deviation. And look what we have here. This is actually lower than the standard deviation of our population here. Now I realize that this standard deviation is a sample standard deviation, which is a little off than the population. But the idea is that these two numbers right here, the 1.52 and the 0.94, they don't match. Unlike the 2.67 and the 2.67 that did match, with standard deviations, wherever these standard deviations were hovering around, they were hovering around the mean of 0.94, right about here. And that is off from what is truly happening in the population. It's a little bit higher. The standard deviation of that population is around maybe 1.7. Again, I chose sample standard deviation, not population, my bad. So I should be seeing something like 1.7, but what I'm estimating is lower at 0.94. That's what we mean by biased. So a standard deviation of lots of samples does not do a good job of estimating the standard deviation of your population. Means do, standard deviations don't. So on page 278, there's a list of unbiased estimators, which are means, variances, and proportions. Biased estimators are medians, ranges, and standard deviations. So that's just the difference between biased and unbiased. Your means of the population don't match the means of the sampling distributions. So there you go, quite a long explanation on how to build a sampling distribution and really what we want to get out of the sampling distribution. Hope that helps.